this module, you will learn about Bohr's model for hydrogen atom. In 1913, Niels Bohr proposed an atomic model that quantitatively explained the features of the structure of hydrogen atom and its spectrum. The postulates of it describe motion of electrons in a stationary orbit, fixed energy of electrons, energy change during transition of electrons, and fixed angular momentum of electrons. The first postulate states that the electron in the hydrogen atom can move around the nucleus in circular paths of fixed radius and energy called orbits. Orbits are arranged concentrically around the nucleus and are also called stationary states or allowed energy states. Electrons are held by the nucleus in orbits by a strong electrostatic force. According to the second postulate, the energy of an electron in the orbit remains constant until the electron absorbs energy to jump to a higher orbit or releases energy to move to a lower orbit. So each emission or absorption of radiation energy represents the electron's transition from one stationary orbit to another. The energy difference between the two orbits is given by equation delta E is equal to E final minus E initial. The third postulate states that the frequency of the radiation emitted or absorbed can be represented by the equation nu is equal to delta E divided by H, that is, E2 minus E1 divided by H, where E1 and E2 are the energies of the lower and higher stationary states, and H is the Planck's constant. The fourth postulate states that an electron moving in a circular orbit has an angular momentum equal to the product of its mass me, linear velocity v, and radius of orbit r, which can be expressed as an integral multiple of h divided by 2 pi, where n is an integer that has the values 1, 2, 3, and so on, and h is the Planck's constant. Since angular momentum can only be an integral multiple of h divided by 2 pi, only certain fixed orbits or stationary states are allowed for electrons to move around the nucleus. Let us now get into more details of Bohr's theory of hydrogen atom. According to Bohr's theory, the stationary states for electron are numbered n is equal to 1, 2, 3, and so on. These integral numbers are called principal quantum numbers. The radii of stationary states or orbits can be given by the expression radius of the nth orbit Rn is equal to n square multiplied by the constant A0, which is equal to 52.9 picometer. This means that the smallest possible value of r, or the radius of the very first orbit, where the sole electron of the hydrogen atom found in its ground state, is equal to 52.9 picometer. This radius is called Bohr's radius. The energy of a stationary state or orbit is given by the equation energy of the nth orbit En is equal to minus Rh multiplied by 1 divided by n square, where n is the principal quantum number of the orbit and Rh is Rydberg's constant, whose value is 2.18 multiplied by 10 raised to the power minus 18 joules. Energy of nth orbit of a hydrogen atom in electron volts is equal to minus 13.6 divided by n square. Thus, the energy of the ground state N is equal to 1 for hydrogen atom is equal to minus 2.18 multiplied by 10 raised to the power minus 18 joules. The energies of excited states can be measured in the same way and represented in the form of an energy level diagram. Note that the energy of the stationary state N equal to infinity is 0. At this energy level, the electron is completely free from the influence of nucleus. In other words, the hydrogen atom is said to be ionized. An electron emits energy as it approaches towards the nucleus, and hence its energy decreases with decrease in distance between it and the nucleus. This principle accounts for the negative sign of energies of electrons in various orbits. Bohr's theory also applies to other ions which are isoelectronic with hydrogen, such as helium plus, lithium 2 plus, and beryllium 3 plus ions that contain 1 electron each. The energies of the stationary states of hydrogen-like species are given by the expression En is equal to minus Rydberg constant multiplied by the square of atomic number divided by the square of principal quantum number. The orbit radii of these ions is given by the expression Rn equal to Bohr's radius multiplied by the square of principal quantum number divided by the atomic number. From the orbit energies and radii equations of hydrogen-like ions, it can be deduced that with increase in Z, the value of energy becomes more negative and the radius becomes smaller. Bohr's theory also states that the magnitude of velocity of electron increases with increase of positive charge on the nucleus, that is, increase of atomic number, and decreases with increase of principal quantum number. Although Bohr's theory is not based on the modern quantum mechanics, it helps to resolve many questions related with atomic structure and spectra. For example, it provides explanation for main limitation of Rutherford's model, the stability of an atom. According to Bohr's model, electrons are held in stationary orbits by virtue of an electrostatic force. That's why they don't fall into the nucleus. The model also stated that electrons are distributed in concentric orbits around the nucleus. The orbits have a specific energy, which decreases or increases during the electronic transition. In addition, it helps to quantitatively explain the emission and absorption line spectrums of hydrogen and hydrogen-like species. Let's see how. According to the second postulate of Bohr's model, the energy gap between the two orbits is given by the equation delta E equals to E final minus E initial. Since the energy of a stationary state is given by the equation En is equal to minus of Rydberg's constant multiplied by 1 divided by n square, we can substitute E final in the energy change equation by minus RH divided by n final square and E initial by minus RH divided by n initial square, to get an equation similar to the expression used by Rydberg. Note that in case of absorption of energy, delta E is positive, and in case of emission, delta E is negative. Thus, each spectral line in absorption or emission spectrum can be associated to transition of states by the electron of a particular hydrogen atom. Bohr's model also shows that the intensity of each spectral line depends upon the frequency or wavelength of photons absorbed or emitted. because of the presence of multiple hydrogen atoms, a large number of spectral lines are observed. The frequency associated with the absorption and emission of the photon can be calculated using the equation delta E divided by h, where h is the Planck's constant. The wavelength can be calculated by dividing the velocity of electron with the frequency of the radiation. The more the number of photons of a particular frequency or wavelength absorbed or emitted, the more the intensity of the associated spectral line. Bohr's atomic model of hydrogen atom, therefore, helps to get most of the answers to the questions prevalent at that time. However, it could not explain the line spectrum of multi-electron atoms, presence of doublets in the hydrogen spectrum when observed through sophisticated spectroscopes, the splitting of spectral lines in the presence of magnetic field, a phenomenon called Zeeman effect, the splitting of spectral lines in the presence of electric field, a phenomenon called Stark effect, the ability of atoms to form molecules through chemical bonding, and the dual nature of electrons both as wave and particle. It contradicts Heisenberg's uncertainty principle, which says that it is possible to determine both the position and velocity of an electron simultaneously and accurately. You have now reached the end of this module. In this module, you have learnt that Bohr's model of hydrogen atom was given by Niels Bohr in 1913. The first postulate of Bohr's model states that the electron in the hydrogen atom moves around the nucleus in a fixed circular orbit of a particular radius and energy. The second postulate of Bohr's model states that the energy of an electron in the orbit remains constant until the electron jumps from one orbit to another. The third postulate of Bohr's model states that the frequency of the radiation emitted or absorbed by an exciting electron can be represented by the Bohr's frequency rule. The fourth postulate of Bohr's model states that any moving body that takes a circular orbit has an angular momentum equal to the product of its mass, linear velocity, and radius of orbit. Bohr's theory states that the stationary states for electron can be represented by positive integral numbers starting from 1 and are called principal quantum numbers. The radius of each stationary state of a hydrogen atom can be calculated using the equation 52.9 multiplied by n square picometer. The energy of each stationary state of a hydrogen atom can be calculated using the equation En is equal to minus RH multiplied by 1 divided by n square, where n is the principal quantum number of the orbit and RH is Rydberg's constant. The magnitude of velocity of electron increases with increase of positive charge on the nucleus and decreases with increase of principal quantum number. Bohr's model explains the stability of an atom as well as the line spectrum of hydrogen atom, thereby overcoming the limitation of Rutherford's atomic model. Although Bohr's model helps find answers to many questions, it has its set of limitations.